In this video I'm going to try to polish off a few things that I started in other videos before I move on to something else. So first of all, I have the RF filter on the front end now soldered down onto the board, and I've also added the capacitor going across both of the inputs to try to filter out differential noise. So first thing to do is to make sure this filter still works, and then also test it at low frequencies to make sure I can still pick up the heartbeat. And I don't see any RF noise, so it looks like the filter still works. And now I need to make sure that I can still pick up a heartbeat even with this filter on the front end. So I've got this old cable back out again. Everything's soldered on this time because I'm sick of having problems with those alligator clips. So let's start recording with this on there. So here it is recording my heartbeat again. The important thing here is that the filter is not stopping it from picking up the heartbeat, which is good. The next thing to do is to rub the cable, see if I can still pick up that noise on there. Alright, that's good. And then I can put on the audio cable and see if I can get rid of that noise. Now I've cut off the bits of wire that have the pennies on them, and I've soldered them onto the wires of the audio cable, which is also kind of nice because now I can unplug my cable without having to solder it down. Now let's see how this works. Let's try moving this cable around and rubbing it to see if I can get any noise in it. So it looks like there is some noise on it, but I think that might just be from my arms moving around, because I'm still picking up a lot of muscular noise here. If I just hit the cable with a pencil, I don't seem to be getting any noise on it at all. So I think this new cable might have actually solved that cable rubbing noise problem. In another video I talked about how thermal noise was a problem. So when my body was attached to the circuit, my body had a lot of resistance, and that resistance has thermal noise, and that thermal noise got amplified by the same amount as the heartbeat signal. But a lot of that thermal noise is higher frequency than the heartbeat signal, so I can put a low-pass filter at the output to filter out not all, but a lot of that thermal noise. And to test it, I made this little dummy load here. I just take the other end of the audio cable and put some 10 mega ohm resistors on the end of it. So I can plug this in, and I have a noise source at the input, and then I can just turn up the microphone volume and start recording. So this right here is the circuit as it is without any filtering at the output. This is how much thermal noise I'm picking up. So what I've done here is I've added a capacitor across the feedback resistor on the output stage that will cause it to act like a low-pass filter. And I sized the capacitor so that its cutoff frequency was about 16 kilohertz, which is the same as that RF filter that I put on the front end. So now we'll record with that filter on the output and see how well this does. So the recording with the output filter does not look all that much different from the recording without the output filter. There is a little bit less noise there, but it's not really too noticeable. I think the reason for that is that even without the output filter, it still has the input filter with the same cutoff frequency. So a lot of that high frequency white noise is getting cut off before it even gets into the amplifier. And now I've made the capacitor 10 times larger, which should make the cutoff frequency 10 times lower. So it's definitely visibly less noise than I picked up at the beginning, but it still doesn't look too much different. Let's listen to the original one and compare it to the new recording to see what the difference is. So it's pretty obvious from that a lot of the high frequency stuff was filtered out, which is good. Now I just need to make sure that that lower cutoff frequency is not going to filter the signal at all. Alright, so everything up until now was recorded a long time ago, and I'm only just now getting around to finishing this video. And it seems like my game was pretty weak at the time, so let's see if I can do better now. Let's start by taking a section of this noise and looking at the frequency spectrum. I don't know why I didn't do this at the time, since my job then was to literally look at frequency spectra all day. But anyway, we can get a much better picture of the noise this way. So here's the frequency spectrum of the noise that was recorded from the control circuit, which is with no low-pass filtering on the output. You can see this large flat section here, which is dominated by thermal noise, which is equal power at all frequencies. And you can see this really sharp cutoff here at the upper end, and this is actually being filtered by the sound card. Now I should have also noticed at the time that the sample rate is 44 kilohertz, which means that any signal above 22 kilohertz is going to get folded or reflected over this 22 kilohertz line. And then it shows up as a lower frequency, which is called aliasing. So to get around this, the sound card filters everything above about 20 kilohertz, so that there's very little signal above 22 kilohertz to alias down to these lower frequencies. Also, 20 kilohertz is about the upper range of human hearing, so there's really no need for any sound card to capture signals above that. And that low-pass filter in the sound card is what is causing this huge cutoff right here. Now, the first low-pass filter that I put on the output was designed to have a cutoff frequency of about 16 kilohertz, which is really not all that much different from 20 kilohertz, so it's not going to be doing all that much good, which we can take a look at here. So you can see we still have this really sharp cutoff at 20 kilohertz from the sound card, and everything is filtered a bit more by the other filter, but see, this is only about 1 dB per line here, so it's really not filtering all that much. Now if we take a look at the last filter, which was designed to have cutoff frequency 10 times lower, or around 1.6 or 2 kilohertz or whatever, we see that that was a lot more effective. Now the y-axis scale also changed when I replotted it, so this is actually 3 dB per step instead of 1 dB per step. So each step on this y-axis here indicates a factor of 2 in the signal power. Now if we take a look at the control recording again, you can see this thermal noise is hovering right between minus 40 and minus 41 dB. I'm not sure what that's with respect to. I think it's with respect to full scale. But anyway, it's between minus 40 and minus 41 dB. If we take a look at the highly filtered signal again, minus 40, minus 41 dB, that's about this line right here. So you can see everything is much more highly filtered at those higher frequencies. Basically everything above 5 kilohertz here is pretty highly filtered. Now something else that you were probably waiting for me to mention is this large amount of noise near DC at low frequencies. And this is called flicker noise, or 1 over F noise, because the shape of the power envelope here goes by 1 divided by the frequency. And this actually comes from a separate noise source than this white thermal noise here. And it's present at all frequencies, but it's much stronger at DC, and at higher frequencies it's much weaker, so it gets covered up by all the thermal noise. Now if we take a look in the time domain and zoom in really close, we can actually see the flicker noise happening. Flicker noise is really low frequency, which means it's going to change slowly in time, so we can actually see it sort of moseying up and down around DC here. It's not going to stray too far away from DC because the sound card still has DC blocking, which has a high pass effect, but we can still see it sort of walking around randomly. Flicker noise in semiconductors is caused by memory effects, which I don't know enough about to explain to you well, but I will leave some links down below for you to look at if you're interested. Actually, getting rid of flicker noise is a little bit beyond the scope of this project, which is really just a nice way of saying I don't really know how to get rid of it. But there are some different amplifier designs that do a pretty good job of getting around flicker noise, like chopper amplifiers. And the type of transistor that's being used to build the amplifier is also really important. Like bipolar transistors have a pretty low cutoff frequency for their flicker noise, about 2 kilohertz. And MOSFETs have a much higher cutoff frequency for their flicker noise. Now the input stage of my circuit has JFETs as the inputs, which I'm assuming are going to be worse in terms of flicker noise than the BJTs. But there's not really all that much I can do about it right now. So for now I'm just going to live with it and move on. I just now tried plugging this in and running it again, and I put 2 9-volt batteries on it, not really thinking anything of it. Turns out in the past I had only been using 1 9-volt battery with it. And 18 volts was just a little bit too much for that poor little TL272 to handle, and it let the magic smoke out. You can see a little shiny spot there where the plastic melted on the package. The datasheet for the TLC272 shows a power supply of up to 16 volts with an absolute maximum of 18 volts. And these are 2 fresh 9-volt batteries, so that was a little bit over 18 volts. So always check your datasheets. That was also the only TLC272 that I had on hand, so I'm going to have to replace that with a different op amp. And this video is already getting pretty long, so I'm going to save that for the next video.